All right, so this video is hopefully going to introduce you to momentum. All right, we'll start off with some basic ideas, and then we'll look at a couple of examples. All right, conceptual examples. All right, so first, present you with momentum. Momentum is usually resembled with a P, and that is equal to the object's mass times its velocity. Now, the first thing is to recognize that this is velocity. Okay. Remember, with kinetic energy, it was always 1/2 mv squared, and that v in the 1/2 mv squared was always just the speed, right? Because it didn't matter what direction your object was going in. All that mattered is that it was moving, and that gave it some energy, that kinetic energy. All right? This one is velocity. The reason why it has to be velocity is because the direction matters. Okay? So if something's moving to the right, we consider it to have a positive momentum, left is negative momentum, so on and so forth. You're going to use vectors here just like you did with the forces and the velocities and accelerations, everything else you've done vectors for. Okay? The thing is that the mass is a scalar number, the velocity is a vector. A scalar times a vector is still a vector. So momentum is a vector, which means it has a direction and it has a magnitude. All right? Now, the big thing about momentum is that if we take a system, so an object or a group of objects, and if there are no outside forces, then momentum is conserved. Okay? This was not always the case with energy, right? Because with energy, we said the energy of an object was conserved as long as there were no non-conservative forces. Okay, but it didn't allow us to work with interactions between objects. Okay, so this momentum is going to allow us to take a full system, and it's going to allow us to deal with the momentum of a system, and as long as there's no outside forces, then it will be conserved. Or in other words, the momentum, the sum of the momentums in the beginning must be equal to the sum of the momentums at the end. And we're going to see that in the next couple of slides. All right? So let's move on to the next one. So dealing with momentum, here's a couple of examples, right? One example is a helicopter. How does a helicopter fly? Yes, I know, I'm an amazing artist. How does a helicopter fly? Okay, well, if you consider what's happening is the propellers are spinning in a circle. As the propellers spin, they push the air down. Okay, now according to Newton's third law, if the propellers push the air down, then the air pushes up on the propellers. All right? Now, if we consider momentum, then we consider this as a system. Okay? In the system, what has momentum? Well, the air is gaining momentum downwards. And so if the air is gaining momentum downwards, then the helicopter must gain momentum upwards. Okay? And so that's your idea of conservation of momentum. Now, of course, a lot of air has to be pushed down because air doesn't have a lot of mass. That's why your rotary has to spin really, really fast, because you've got to get those propellers to push a lot of air down, okay? Because momentum is mass times velocity. So the air going downwards will have a very big velocity because it has a very small mass. The helicopter has a very big mass, and so it will have a very small velocity going upwards. But putting those things together, small mass, big velocity of the air, needs to equal the big mass, small velocity of the helicopter. All right? Another good example is an astronaut. So here's my astronaut. He's in outer space. You can tell it's an astronaut because he's wearing a big helmet. Yes, he does have arms. No, he doesn't have hands. So there's my astronaut. He's in outer space. What would happen if he took a baseball and he threw it? Well, initially, we have zero momentum, right? So if the ball gains momentum going to the left, that's a small mass with a high velocity, then to balance that out, the man is going to have to travel over to the right. okay? Because those two momentums need to add up to my initial momentum of 0. Initially, there was no momentum. The astronaut was at rest, the ball was at rest. In the end, I've got the ball traveling to the left, so to balance that out, I need momentum to the right, which is going to be my astronaut. Now, of course, the astronaut has a much larger mass, so his velocity is going to be small. Okay, conservation of momentum. All right, we'll look at one more situation. The other one I can think of right now that is also dealing with space travel, I suppose, is your rocket. How does a rocket gain speed both on the ground and in space? In space, it doesn't even have anything to push off of, right? It's easy to think of this one, well, at least he's pushing on the ball's pushing on him. But this one's a little bit harder to consider because what is it pushing off of? Well, it's pushing off of the fuel, right? The fuel is flying out of the bottom. The fuel has a downward velocity, okay? So you've got the mass of your fuel with a very high velocity being shot out of those thrusters. So in order to conserve momentum, what has to happen to the rocket ship? Well, the rocket ship of a very large mass is going to have to gain a small amount of velocity. Okay? That's why when your rocket ship takes off, if you've ever watched a rocket ship take off, the beginning is very, very slow. Even though that fuel is blasting out of there, out of the bottom, it takes off very slow because it gains a very small amount of velocity as that stuff is flying out. But again, this is conservation momentum. The mass and velocity flying downwards needs to be balanced with the mass and velocity going forwards. Okay? Therefore, the rocket ship is allowed to move forwards. The fuel and the explosion is then all moving downwards. So these are all situations where conservation momentum allows us to do something. All right? I'm going to go on to the next slide, and the next slide is going to have a video. I want you to watch the video and see if you can explain how conservation momentum applies to this specific situation. All right? All right, so in this first video, we've got a guy shooting a gun, and I want you to pay very close attention to the gun and what happens when he shoots the bullet, and then see if you can figure out how this applies to conservation momentum. You see it? Okay, there's going to be one more guy. Watch closely in case you missed it the first time. We're going to watch it again. Here we go. All right, so hopefully you saw that. Hopefully you saw that in the moment that it shot the bullet, what happened to the gun? The gun went backwards, all right? So here we go again. We'll talk through it. The bullet is very small, right? The bullet is very small, and it gets shot out of the gun. So it has a small mass and a large velocity, okay? Now the gun is the thing that's colliding with the bullet, right? You've got the gunpowder. The gunpowder is going to push the bullet in one way, but if the bullet is gaining momentum, something else has to be getting momentum in the opposite direction. And the thing gaining the momentum in the opposite direction is the gun, right? And so the gun is going to have momentum in the opposite direction. The gun's going to go backwards. But because the gun is so big, a big mass, then its velocity is going to be very small in order to conserve the momentum. All right? You can, of course, also use Newton's third law to explain this, but the exact values of the mass and the velocity are related through conservation momentum. Let's look at another one. This is a similar idea, but this one is a small grenade. Okay, what did you see? When the grenade blew up, hopefully what you saw was all the pellets going in all different directions. Okay, now in this situation, it's not a simple gun and bullet. You've got initially a grenade that has zero momentum. So in the end, you've got to have zero momentum. As the grenade blows up, you're going to have some of the BBs flying to the left, some of them flying to the right, some of them flying up, some of them flying down. Of course, here, the ones that fly down are going to bounce off the ground and fly back up again. But the sum of all of those directions, all of those vectors, has to add up to 0. If it doesn't add up to 0, then momentum won't be conserved. And so again, even in this situation where you have, I don't know how many, 20, 30, 40 little pellets flying in different directions, add all those up, the velocity, the momentum, all of that put together will add up to a momentum of 0. All right? I got one more for you here. Okay, this one's a little more interesting. See if you can figure out how momentum applies to this situation. Jumps into the water, and whoa! What just happened? Yeah, he really just did that. What is happening here? How is this momentum? Hopefully, you can't see this. You can't see this in the picture, but what happens is he has webbed feet. The bottom feet right here that are hitting the water, those webbed feet are able to push down large quantities of water. Now, if the water is gaining momentum downwards, then something else has to be gaining momentum upwards. And what it is his body is getting pushed up through the legs. All right? And so he pushes the water down. The water pushes him up, Newton's third law, but the mass of the water going down and his mass going up have to be fairly close. Now, he's pushing down pretty hard, which is going to be just enough for him to maintain his momentum above the water. All right? So again, you have a mass of water going down, his feet and therefore his body being pushed upwards. The momentum must be conserved. All right? Now, in case you're wondering, yes, when he lifts his foot up, he's able to close his toes and pull it out of the water with very little resistance. And that's why there's a net force downwards, because as soon as he starts pushing downwards, he opens his toes again and the webbed feet push down, and so you get more resistance. So it's a pretty cool application of momentum and or Newton's third law, but overall, that's what we wanted to look at. So there's your introduction to momentum. Watch the next video, which will show you a lab that has a couple of different applications of conservation momentum and when momentum, well, I guess momentum's always conserved, but when is energy conserved and when is it not conserved? All right, that's it.